Hello everyone, welcome to the first of a series of videos looking at gas laws. Today specifically we'll be looking at Boyle's Law. Now before we get into that, let's have a little background as to what the gas laws are. So the gas laws are three laws used to explain why and predict how a constant mass of gas would behave under different conditions. These conditions include changes in pressure, changes in temperature, which is the absolute scale that is used, the Kelvin scale, and changes in volume. Now there are some assumptions that we do make during our calculations. The first is that the mass is constant. The mass of air we are considering is constant, the mass of gas. It has no volume, so we treat it as a point particle. It has no volume, the volume is negligible. All collisions between gases are elastic collisions. They move randomly in straight line. This means that there is no net force acting on the particles. Therefore, no intermolecular forces of attraction, and the average kinetic energy is directly related to the temperature of the gases. Now let's move on. In reality, we have real gases, but to suit our calculations, we treat them as ideal gases. Now let's see the characteristics of real gases and contrast them with those of the ideal gases. Real gases have their own volume, so once a substance exists and has mass, it has a volume. However, we treat it as an ideal gas which has no consequential volume, so basically no volume. Real gases have intermolecular forces of attraction, while ideal gases have no intermolecular forces of attraction. Their collisions are elastic, while real gases have slightly inelastic collisions. Ideal gases, they move randomly in straight lines. There is no net force acting on them. And also the average kinetic energy is directly related to the temperature, as we said. Real gases, they behave most ideal at low pressure because the farther they are apart, the volume becomes very negligible. And at high temperatures, again, at high temperatures, they move faster, so those intermolecular forces of attraction will be very minimal. Now let's look at our first law, Boyle's Law. Boyle's Law states that pressure is inversely proportional to a change in volume at constant temperature. Now here we have the expression and the equation which says pressure is proportional inversely to volume at constant temperature. Pressure is equal to some constant times 1 over volume, or multiplied by 1 over volume. In this case, the volume is the independent quantity and pressure is the dependent, since no new mass can enter the environment. So let me explain this a little. If you have a container of gas, there is no way you can change the pressure while the temperature is constant without actually changing its volume. So you need to change the volume in order to get the pressure to change. So when temperature is constant, volume becomes the independent variable that needs to be varied in order to get some response in pressure. When plotting a graph, we would plot pressure against volume, which will give us a curve. But if we plot pressure against 1 over volume, we get a straight line. So they are proportional. I have a simulation here. Let's look at the simulation. If we recall, the pressure exerted by the gas is due to it colliding with the wall of the container that it is in. So what we're going to do is look to the top left of my screen and let's see if we can notice the collisions per picosecond. So there are basically 0 collisions per picosecond per 5 picoseconds. And we see here where the gas occupies a large space. So this gas basically occupies all of this container. All of this container is its mean volume, meaning it goes back and forth, it bounces in all of this space here. But as we add the amount of particles that we'll be using, so we will be using 100 light particles plus that purple particle here just for contrast. So the first thing we notice is that we have more collisions happening. Look to the top left of my screen. Also the volume that our first gas particle occupies becomes much less. It is covering less space per unit time. Now if we vary our volume by decreasing our volume, according to Boyle's law, we expect our pressure to increase. Will this happen? As we said, pressure is due to the particles actually colliding with the walls of our container. So we see that as we decrease the volume, we have more collisions happening. We have 126 collisions happening per every 5 picoseconds. That means the pressure has increased while our volume has decreased. So the mean space in which our particles get to move decreases. Here we increase the volume and we see the opposite thing happening where the particles have more space and therefore they hit into the walls of the container less frequently. Let's see if we measure the collision rate. It was 126 before and now it decreases to 73. However, you see that our purple particle here has more space to bounce around. That means our volume increased, our net volume increased, but our pressure it decreased while having temperature constant. Now this is what Boyle's law really is about. Let us do a question. Let us attempt this one. It says a gas occupies 12.3 liters at a pressure of 40 millimeters of mercury. What is the volume when the pressure is increased to 60 millimeters? So let's go ahead and write down what we do have. We have pressure 1, we have pressure 2, so we have the pressures for the first and second instance. We have the first volume, but what we're trying to find is the volume in the second instance. The next thing we do is to write down our known formula, which says that pressure is equal to some constant K multiplied by 1 over volume. Or we can say pressure times volume is equal to some constant at constant temperature and mass. So in our first instance, we can say P1 times V1 would give us K, which is that constant. Now we would expect that in our second instance, P2 times V2 would also give us the same constant. Since we are working with the same mass of gas at the same temperature, we should get the same constant K. And if we're going to get the same constant K, we can say K is equal to K. Now, if K is equal to K, and P1 times V1 is equal to K, and also P2 times V2 is equal to K, then we could go even a step further to say that P1 times V1 is equal to P2 times V2. And having said that, we can now set out our values in our equation. Both sides, the only unknown here is V2. What we would need to do now is actually make V2 the subject of our formula. After we have done that, remember our units, and our answer should be 8.2 liters. Now I hope you found this video helpful and the explanation extremely helpful also. The next law we will be looking at is Charles' law, so stay tuned for the next video in this series.